Hello, hi everyone. Okay, so welcome to our lesson today. So we are going to be working on functions, and this time around we are not going to do the elementary approach of functions, but we are going to do what I can refer to as an abstract approach of functions. You see, so we are going to actually follow the same pattern of what we did in our first year introductory course on this area. But now we'll try and make things a little bit more abstract, you see. So this course is for those who are taking abstract courses like linear algebra, real analysis, and many other different areas of mathematics, you see. Okay, so the first thing that we are going to uh, open the session with is we're going to provide a definition of a function. See, so we'll understand what a function is and then give few examples of what functions are. You see, so given some sets A and B, the function uh, usually denoted for G or H, etc. Um, is a rule that assigns uh, each element of some set, let's say A in this case, to some unique element in another set. So let's say this set is B, you see. And if this is the case, we write f is a function which maps A to B, like that. You see, so a function is just an assignment operator which takes every element that resides in one set and assigns each and every element to some element B in B, which is unique. You see, like that. So that's exactly what functions do. They just take a whole set and map it to another set, which you can refer to as some set B, like that. So it's good to make sure that you understand all this terminology. You see, so to give this a visual illustration, we can actually represent functions as below. So the set A can be represented as a Venn diagram like this, as well as the set B. We can also represent it as a Venn diagram as that. You see. So what a function does is that it takes the whole set A and it maps it to the set B like that. So that all the elements that resides in A are mapped to some subset which resides in the set B like that. You see, so that's what F does. So F simply takes things that are in the one set and it maps it to a subset of some set B like that. You see, so there are special names that we usually use to refer to this set. So the set such as A in which the elements to be assigned are stored, we refer to this as the domain. You see, while it's the set B in which consists of all the elements which we assign to is called the codomain, like that. You see, then this small set in which everything that is in A is mapped to, we refer to that as the range. of the function, like that. So these are basic things that you have to understand when it comes to functions, that a function is just the rule which assigns everything that resides in A, in a subset A, to some things in B. You see, but whatever element that is in A, it is always assigned to some unique element that resides in B. So that's exactly how we define the function, you see. So examples of functions include uh, 1, f of x equals to 2x plus 1, which maps the real numbers into the real numbers, like that. Then 2, also we have other different types of function, f, which is just 3.52x plus 1, which maps real numbers to some set B, which is a subset of real numbers, like that. So all these are different types of examples of what we refer to as functions. But basically speaking, that's what we have to know about function, that function simply takes everything that is contained within a particular set and maps it to something unique in another set. And you also must familiarize yourself with that kind of terminology. You see that? Then there can be some useful notation that can be used quite often when we want to refer to the domain and range. So let's put that down. You see that? So 1, so the domain of f is usually denoted by dom of f, like that. You see. So when we want to refer to the domain of some function f, then we shall use that notation. Then the range of f is usually denoted by, sorry, by range of f, or range in full of f, like that, you see. So there will be some instances where actually we're going to use that notation. So it would be good if we can just lay it at the start of our discussion, you see. So basically speaking, that's what we do, how we define a function, and these are terminologies associated with functions, you see. So the next thing that we want to talk about now is every time when we introduce new objects in maths, one thing that comes afterwards is to see that what sort of operations can we introduce within that space of objects. You see that? So now we've created a space in which that space, the object contained inside, are functions. So what we want to see now is in this space, what possible operations can be defined there, which are well defined, and also can allow us to build new functions from the old ones that we have, you see. So this will bring us to one of the common operations of functions known as composition. So what is composition? You see. So if f from A to B and g from B to C are functions, then we define the composition of f and G as the function. So if every time you're given two functions, uh, f and g like that, then the composition of two function is usually denoted as g o f, which is now a function which takes us from a up until c, like that. You see, so that's how exactly we can define a composition. So to understand this thing geometrically speaking is let's try and represent functions maybe as arrows. So let's represent f with an arrow where f starts from a and finishes at b, like that, and then g as the function which starts from b and lands at c, like that. Then the composition, or what we define as a composition, is a function actually which uh, takes us from A and lands at C. So we define such a function as G or F. So always make sure that you pay attention to the order, because if the two functions given are defined that way, then the composition must be G O F, not F O G. So if you write F O G, it will be completely wrong. You see. And this is clarified mostly by now when we actually define what is the composition, you see. So we have already defined that the composition, it is the function f of g, it is the function g of f, which is defined that way, such that, see, such that g of f of a is just the same thing as saying g of f of a, like that, you see. So this is how we define the composition of functions. So it's also not something new. It is something that already we've come across in the elementary discussion of functions. So now it's just that we're just becoming more abstract. So I won't give any more examples. If you want to see more examples on this, you can go and check previous videos that we made on this subject. You see, so our goal now is not to go back to elementary discussions, but we want to just keep everything a bit more abstract, and that will be it for this section. You see, so okay, so now we see that we have actually defined uh, this thing of composition. But now there is one thing that you should know about composition. So the composition is the following property. You see. So you see. So if f from A to B, G from B to C, and H from C to D are functions, then we have that um, so H O G O F is equal to H O G O F. So what you should know is that every time when you are composing three functions at the same time, so the order in the first two that you compose doesn't matter. So the order in which because composition only works for two functions, so which means you can compose any two functions at the same time. So one thing that you should know is that the composition it always satisfies this property that if you're composing three functions, any two next to each other that you join first will not affect the outcome of the composition. You see that? So by this, we mean that composition of functions is associative. You see that? So this result simply tells us that the composition of function is something which is an associative operation, because it doesn't matter which neighbors do you join first before you put onto the other functions, like that. So these are things that you must make sure that you understand pretty well when it comes to the composition of functions. So just again, I'm not gonna pay much attention on showing you how to evaluate all these kind of stuff. I'm just gonna keep it here for now. But anyway, just maybe to do a problem that may be actually a trickier one to handle might be as follows. You see, so you might be saying, given the function f, which takes some number m, n, and then it gives us another coordinate, which is just 2m minus 1, and then m plus n minus 3, and also given another function g, which takes mn, and it gives us 5m plus n, and then 2m minus 1. Then they might say find the following results. So they might say find FOG and GOF. You see. So one might ask, but how can these two be valid at the same time? How can these two be valid at the same time? So sometimes already we've seen that FOG and GOF are two different things, but there are some instances whereby one can be valid while the other is invalid. There are instances where both are valid. So when are these valid? You see. So what you should to understand why these are both valid, you have to pay attention that we have that. So what you should pay attention is that if you look clearly, you will see that the function f defined above, it's something that takes the set R2 and maps it to R2, and also g is the function which takes R2 again and maps to R2, like that. So if two functions work on the same domain and range, then the composition can be done in all different directions, but still the outcome is not guaranteed to be the same. So these two need not be equal to each other. So by this, we mean composition is not a commutative property. So that's what we have to understand here. So this example is serving as a demonstration that, yes, indeed, you don't have to expect this thing operation to be commutative. You see. But now, how can you evaluate FOG? That's the question now. You see. So how can you find FOG? You see. So one of the things is we want to find FOG like that, and we understand that this function can only take a coordinate mn like that. So according to the definition, we know that FOG is just the f of g mn, like that. You see, so which means in fact in f we're going to put gmn as an argument. But now what is gmn as what is the output of gmn? So if you look by definition, g is a function which is such that when you give it mn, it returns that. You see, so when you give it that, it returns that. So you get f of 5m plus n, and then as well as 2m minus 1. Like that. You see. So now these two guys here, you can actually refer to this as a new m prime. You can refer to this guy as a new n prime. So which means now what you're trying to evaluate here is you're trying to find f of m prime n prime. You see. But now what is f of m prime n prime? according to the definition. So according to the definition given, we know that f of m prime n prime is just this. So it is equal to 2m prime minus 1. So it's going to be 2m prime minus 1. And then m prime plus n prime minus 3. So m prime plus n prime minus 3. But we know what m prime is. So m prime, if you look, it's 5m plus n. So you have 2 of 5n plus n, then minus 1. Then m prime again is still 5m plus n, while it's n prime, it's plus 2m minus 1, then minus 3. So when we simplify, what do we get? So we get here 10m plus 2n minus 1, and then here we have 7m, and then plus n minus 4. So this is the output of that composition. So also you can do the same thing for the reverse, and you will see that at the end of the day, it will be clear for you that f of g is not equal to g of f. That's composition is not commutative. You see, so those are things that you must make sure that you understand as it comes to the discussions of functions. Then the next thing that we're going to go for is now we have understood what functions are and an operation that can be done with functions, or an operation that can be performed in the function space. The next thing that we're going to look at now is none other than the identity function. So the identity function. You see that? So the identity function is a function which maps a set, say A, onto itself. You see, so an identity function is a function which maps a set A onto itself. You see, so if the set is A, then the identity function is denoted by 1A. So we also have another function which is called the identity function, which for some set A, we usually denote it using 1A. And it is always a map from a set to itself, you see. And the identity function on A from A to A is defined as follows. You see. So this function that we refer to as the identity function, this is how we define it. You see. So 1A is a function which is such that when you put anything that is in the set A, it gives you A back. So for everything that is in A, that is what you're always going to be getting. So when you take A and then you put it there, so it returns that element back. So that's what an identity function is. So it is one of the special functions that you must know as we come and deal with subjects like abstract mathematics, to always know that they exist for any set. They always exist this function called the identity, which is defined that way. See, so it's always good to know such things about the identity. Then the other thing that you should know is this. You see, so and okay, let's move to it this way. Given if f from a to b is a function between the sets a and b, then we have the following. So if f is a function between a and b, then we have the following result. So if you take f and you compose it with a, you always get f back. And this is the same thing when you compose 1b with f, like that. So the identity property is this property whereby when you compose it with a function, it leaves the same function as it is, you see. So that's it behaves like the element 1 in the real numbers when you multiply. That when you multiply by the element 1 in the real numbers, it remains the element remain fixed or remain unchanged. So also the identity function, it has the same property that when it multiplies the functions either from the right or left, then that remains unchanged. So to see a proof that this is indeed true, so let's prove that yes, that is really indeed true. So what we're going to do now is we'll say suppose f of a is equals to b with a, any element that is in a, and b, an element of b. You see, so let's suppose that this is true. Then now, what do we have? Now, what do we have? So now let's find what is f of 1a with argument a. So we know by definition of composition, this is just the same as saying f of 1a of a. But we know that when you the identity works on the element a, it returns it back. So we just get f of a. So we get b. You see, like that. So that's what we realize. Also, again, you can apply the same technique again. So if you say fb or f with the argument a, what do you get? So you get 1b of f of a, like that. But now you'll get 1b of what? So f of a by definition is b, so we get 1ab of b, but the identity always returns the same element like that. So therefore, we have that. F of 1a is just the same thing as f, and it is just the same thing as 1b of f, you see. So these are basic things that you should know when it comes to functions. That every time when you're functions, you should always know all this basic stuff about functions, you see. So to avoid making this lesson unreasonable long, I will just cut it here for today so that you may take some time to try and absorb all this that we have discussed in this class. And then in our next lesson, we are going to start looking at the three types of functions that one can encounter in the space of functions. You see, we will discuss things like injective functions, adjective functions, and bijective functions. Otherwise, thanks for watching. See you next time.